Well, thank you to the organizers for having me. So this paper has limited connections to market design, but hopefully you'll see it's a methods framework and it can be applied to a number of contexts. So let me just motivate the problem first. So fundamentally, you've seen this in a number of papers, both yesterday and today, that heterogeneity is kind of a key element, including kind of the last paper that we just saw. Okay? There's multiple reasons why you want to take heterogeneity seriously. Some of those have to do with inference and bias. What I'm going to try and focus on is where you really care from an economic standpoint about the heterogeneity. If you want to use it for the construction of some economic quantities of interest. Right? I'm going to focus more on the practice of doing this rather than on the theory. And if you're interested, there's a lot more in the paper on the theory side. This is, based on joint work with Max and Tengyuan, who are both at Chicago. It's going to build on our recent paper, which provides kind of convergence rates for estimators that have deep nets in them. So let me just stop. Let me motivate first why we need structure. I've added these couple of slides in just to give you an idea of why structural models are important in this world where we've got deep learning and machine learning. And that's going to motivate how I want to think about incorporating deep learning. So this is a chart from a paper that I had with JP Dubey. We ran a pricing experiment where we randomized prices at a firm from $19 to $399. Don't ask me how we got the firm to do it, but they did it. Right? And imagine now that you want to use this to estimate the optimal price. Okay? A really simple toy model. So you say, oh, I want to take this data. You've got this data over here. I'm going to estimate the demand curve from this data, plug it into a very simple profit function, and optimize to get optimal profits. And you decided to look around and say, what's your favorite ML tool? And you saw deep learning and forest. They're all kind of equivalent in some sense. So you chose to use a forest. I want you to just guess as to what the optimal price would be for this demand. And I'll tell you what the random forest-based profit maximizing price would be. It's going to be infinite. Always, not sometimes. If you use a random forest to estimate demand curves, you're going to get infinite prices always. Why? Because the way forests work they are basically a collection of trees. And the way trees work, they are kind of simple partitions of the data space. So when you want to extrapolate, it's going to take the closest thing here and say demand's going to be stuck at that point. So you can keep increasing demand or keep increasing prices. Demand will always be positive, which means you go to infinity. Right? The only way around this is to put some shape constraints on your demand system. That's what I'm going to call structure. Right? So if you don't put in some economic thinking, you're going to get infinite prices. And this is not just for forests. You can run into weird problems with deep nets, with boosting, with whatever machine learning tool you care about. Right? So don't do that. Okay. So the model that I'm going to kind of think about is going to be encapsulated in this loss function. And you can think about this as being any structural model that generates a loss function. So a loss function could be a negative log likelihood. It could be a GMM objective function. I am going to be completely agnostic. The only requirement that I will have is that this loss function is smooth, because I'm going to take derivatives, right? So I need this to be smooth, and that's pretty much it. So any parametric structural model that you can think of, whether it's BLP, whether it's some dynamic model, it doesn't really matter as long as you can write down what that loss function is. I'm also going to assume that you care about these structural parameters, theta, that are subscripted by I, where I happens to be the unit of analysis. So for me, I'm a marketing guy. I think about consumers. But it could be firms, whatever the unit of analysis is. Right? You'll also notice that I've not said whether this is cross-sectional or panel. In my world, it makes no difference. So you can think of Y as a set of outcomes, T as a set of treatments, right? So T could be prices, Y could be, purchases or sales or whatever else. Okay. And if you've got panel data, just move them into columns and then call them rows. Right? It makes no difference. Okay. So what's the thing that people usually do when they're faced with heterogeneity of this form? They ignore it. That's the simplest, easiest solution. Still incredibly popular as a technology. For most part, kind of works reasonably well. Our idea is going to use an old idea. So this is not new. We're going to project our structural parameters onto a vector of characteristics X. And X could be high dimensional, right? So it could be thousands of things that you know about your customer, for example, or a particular firm, or whatever the unit of analysis. By the way, stop me at any point if you have questions or thoughts.
Oh, question.
Yeah.
So why not do a fixed effects and estimate theta I and then project?
Very good. So you could do that. So in order to do fixed effects, you would need panel data, obviously, but imagine that you don't have panel data, fixed effects goes out the window. You could do random coefficients. I'm going to argue, and we've had this discussion before, that this will nest random coefficient models. Right? I'm not going to have this, actually, I had this discussion already, but I'm going to have this discussion offline. You could, if you did have panel data, you could do the projection. We're just pushing the projection in. And I'm going to argue that this approach is going to be more scalable. So if you're going to do that anyway, you might as well step back and do it.
Just following on that, if you do have panel data and there's discreteness in the choice set, so each individual's estimate of theta I is going to be biased. And so when I go to do the projection, what happens?
You mean in two steps? In this case,
what you're saying is, what your answer going is, I'm going to get a theta I for each guy, and then I'm going to project it out.
No, I'm saying I'm not going to do that. I'm going to do it all in one step. Right. Yeah, so I'm getting away from the fixed effect estimation issues completely now. By just plugging it in directly. In particular, so this paper is about using, so here we don't know what this functional form is and how to deal with it. So we're going to take each structural parameter and think of that as emerging as a deep problem. Okay, so that's the framework. This is literally it. So you take any model that you care about, any structural model, take the parameters of that structural model and say each of those parameters is a deep net, or the vector is a deep net itself. Okay. Now the challenge, of course, is how do we do inference here? And what do we do with this? How do we implement this framework? Here's a way of thinking about this. So typically we think of deep nets for prediction, right? So if you take any of the work that's coming out of CS or firms like Google, they would use, these would be the outputs. So there will be Y here. Instead, what we have is there are a set of X's that predict your type, and your type or your thetas go into a model layer, which is completely determined by the economist or the econometrician, right? And then you get your loss function or your likelihood or your GMM objective function. So this part is what we usually do. All we have done is we've added a deep net on top of it. Okay. Okay. The estimator is then incredibly straightforward. Looks like this, and it looks complicated. It is incredibly simple to implement in standard software like TensorFlow or Torch. If you're making a choice, if you're a user of R, for example, I would recommend using Torch. If you're a Python user, you can use PyTorch or TensorFlow. It doesn't really matter. And I'll have a package out like in the next 2 weeks that you can all play around. Okay. Why use deep nets instead of using something else? There's a few reasons. One, we have a good understanding now of what deep nets are capable of. Obviously, we know that they can distinguish between whatever, hot dogs and not hot dogs, but also they are universal approximators. They're smooth, which is phenomenal because it helps kind of do math around them much in a simpler, easier way. They're scalable, and by scalable, I don't mean that, so typically there's this misconception that deep nets require a ton of data. They don't. Think of deep nets like as splines, if you will, or as polynomials. So if you could use a 17th order polynomial, but if you had limited data, you'd say, I'm just going to use x and x squared. right? The same thing goes for deep nets. If you have limited amounts of data, just pare the complexity of your deep net down, you'll still get a meaningful depiction of heterogeneity. And you'll see in my applications, we're always going to be using tens of thousands of observations or thousands of observations, not millions, right? And it will still work.
So I have a question.
Yeah.
I'm not sure how to turn this on. But if you're using torch or PyTorch or TensorFlow to estimate these models of splines, splines have sparseness that should make the estimation easy. But a lot of the neural net algorithms don't use sparseness, and so they would seem to be inefficient. But do they take advantage of the sparseness? And
they do. So you can think of the lasso as being a special case of a deep net, actually. And so sparsity is inbuilt. So there's various ways in which you can regularize a deep net. So like a lasso is just a regularized regression. Now, so a deep net is also regularized. There's multiple ways. We don't recommend or use L1 or L2 regularization. We use implicit regularizations. If you're not familiar with this, my co-author Tengyuan has this incredibly insightful paper came out in the Annals of Statistics.
That's not my question. So I mean, it's a good point. But my question is, regardless of how your regularization says mathematically, when you're actually implementing it, some of the matrices, like for splines, are going to be sparse.
That's perfectly fine.
Actually use the sparseness of the matrices with sparse matrix classes, or does the implementation just create a dense matrix?
You can do it. Yeah, you can.
In the case it uses dense matrices.
Oh, you don't need to. You can use sparse. You can use sparse matrices. You can use any form of. So that's a data issue, right? So the deep net is an incredibly flexible. How the data comes in and what you do with it is completely up to you. You can add so what I call encoder layers. So if you have sparse matrices coming in or a mix of sparse and dense matrices, you can do that too. But we can have a conversation offline about how the implementation works for different types of data. But just to complete the thought, implicit regularization comes from the fact that if you start off a deep net with all zeros for your weights in the deep net will never move because all the gradients will vanish to zero. So using that intuition, if you start off your deep nets with really small numbers, that acts as a regularizer. So initial conditions are an implicit regularizer. There's a paper in Annals of Stats that Tengyuan has that kind of explains how this works. Okay, the last piece is the most important piece is you can do something like this. This is way harder to do if you're doing it with, let's say, trees and forests or some other universal approximator, right? Here, this thing becomes simple. So here's a simple example. Imagine that you're estimating a binary choice model. We've seen multiple versions of this. Yeah.
Can you explain why it becomes harder to different kind of?
Yeah. So let's look at this, right? You'll see this in this context. So imagine that I've got this model, standard binary choice. Now I want the intercept and the slope to be different across units. This I can write here, and everything else is already done. Now imagine that you wanted to do this with forests. So Susan and Stefan have this paper on generalized random forests. You'll have to construct moment functions, and the splitting rules will have to depend on, you'll have to derive the influence function to construct that estimator. Right? It's doable. Nothing's not doable. They're just all different approaches. This is just easier, and it's going to be completely automatic. What I'm going to show you is you don't have to do anything. You just say, this is my model, and go. Right? And the rest just happens as if you're running like a program like LM in R. That's it. That's the level of complexity for using this stuff. But the nice part about this is I want you to notice all the interpretation of these things. Everything is maintained, right? So you can construct, if you want to do welfare calculations and you want the log sum, well, that's just the log sum. And it has alpha and beta inside it. You can do whatever you want with it, right? If you want to do willingness to pay calculations and you want to do, let's say, a ratio of beta, beta over alpha, something like that, you can do that too. Okay, so how does this work? Well, there's three pieces. I'm going to just give you the intuition. Again, if you're interested in the theorems, they're all in the paper. The first part's going to be this idea that these fixed effects can actually be approximated, right? That's one assumption. We're going to call that an approximation. The other two will deal formally in the paper, like whether or not the deep nets can approximate whatever this true function is. And second, can we actually estimate that deep net? Those are two separate problems, right? So the typical way that proofs of these things flow. So the first thing is this approximation really good, or can we think of this as being good? You can't see this here, but this is all the data that Facebook says they have about you. There's about 50,000 variables. Now you might say, oh, maybe there's another unobservable that Facebook doesn't have. Sure, but that unobservable would have to be uncorrelated or orthogonal to the set of data that Facebook does have. Otherwise, non-parametrically, I'm going to pick it up. Right, so good luck with finding what that unobservable is. Right, so this is just to say that the set of data that we typically now have about units is fairly exhaustive, not necessarily complete, but getting there.
Seems like we have so much data that the worry would be that treatment would change some of these X's if you did a counterfactual or something like that, right? But you're over controlling.
Like your age?
Well, I mean, I would say like age and gender are probably things you don't want. They're probably pretty immutable to the policy of Facebook, but they have your browsing history or whatever, you're sort of tossing it in there, then
so that's
yeah.
Perfect, right? So that makes me say that's why we need people like you and me, right? So if you are doing this mechanically, I would say that would be a real problem, but that's why we need somebody to think through what the structure of the problem is and partition the data into what would move and what wouldn't move, rather than blindly throw everything into a black box. So that's basically my argument. Okay. Again, I'm going to skip all this, but basically to show you that we have rates, and the rates are fast enough that you can actually do something useful with this. In particular, we want to do inference, right? So if we want to use this in doing scientific research, I need to be able to show you that we can get standard errors or confidence intervals or something else like that. And for that purpose, we have to define kind of the object that we care about. So we've come up, and we actually generalized this, but I'm going to show you this because we already have the results for this. Imagine that you care about the expected value of some function h, which has theta inside it. So this could be something like, what are average profits? What's the average elasticity? What is the average welfare gain? Whatever you want to call it, like whatever you want to do. It could be counterfactuals, like we have seen in the last couple of days, or just welfare measures or whatever, anything that you want to compute after the estimation is done. The paper shows you that there is a generic influence function that you can compute that will give you the correct variance terms for these things. So I'll give you standard errors or confidence intervals. And the key part of this thing over here is it depends on the function, the derivatives of that function with respect to the parameters, the gradient of the loss function, and the expected Hessian of that loss function. And what's really nice about this influence function, it nests other influence functions that we already know. So if you're familiar with the causal inference literature and you've seen doubly robust estimators, like I don't know if Whitney's here today, but like the stuff that Whitney's been working on, for the places where we know the influence function, you get this to pop out. So if you took a binary treatment with a continuous outcome and computed what the doubly robust estimator would be, it's exactly the same. Brian Graham has a paper with slightly different assumptions where he finds the efficient influence function, comes right out with this one here. So the ones that we know that where the model is complete and you compute what the efficient influence function is, we have so far found them all to kind of pop out of this. In other cases, we can't guarantee that this is the efficient influence function, but it is an influence function. And so at worst, you're getting conservative standard errors. Okay. Again, key point here is you don't have to code any of this. You don't have to take these Hessians, gradients, nothing, because in TensorFlow or in Torch, all of these can be done with automatic differentiation, and they are exact. They're not approximate. They're not like finite differences or numerical stuff. They're all exact. So it just saves you math, if you will. Just small point, like the old, not the old, but kind of the standard approach to computing influence functions is to do it by hand, right? So you write down the problem, you solve the math to find the influence function. Once you know and can characterize the influence function on paper, you then code it up. This approach, why is it working without actually doing that? It's because of the realization that you never actually need to fully characterize the influence function. You only need to evaluate the influence function point-wise on the observed data. So it's just a practical trick. Because of that, again, for technical people who are interested in this, what would be a functional derivative like a Ghetto derivative becomes a regular derivative because it's point-wise on the data. Okay, so I have till 11:20.
Yeah, 25, yeah.
Okay, so in the next kind of half, I'm going to walk you through two applications, unless we can actually a different paper in there too. But the first is going to be a replication of one of my colleagues' work, or two of my colleagues, Marianne Bertrand and Sendel's work on advertising. There's a QJE paper. And then a second application to the SNAP program in California. I'm going to show you both. The applications are chosen to highlight what this framework can do above and beyond what we typically know in the causal inference. Okay, so what is the Bertrand et al. Paper? It's an experiment that was run in South Africa for short-term loans. And the question was, what's advertising worth? So what they do is they randomize elements of advertising, but they also randomize interest rates that go as offers to potential customers. And the paper is more about like looking at the trade-off between the advertising elements to see whether or not a match between your race and the picture of the person on the ad, does that matter? If there's a female in the ad, does that matter? If I say something about, the duration of the loan or something else, does that matter? So the bunch of characteristics of the ad and how do people trade off against the interest rate, right? That's what this paper is all about. Okay, the first thing, we implement our framework and kind of the results. This is more just a check. Because it's a randomized experiment, it should be that our results coincide with theirs. So first we replicate their results using no heterogeneity, which is what they have. And then we provide confidence intervals, and essentially our estimator or their estimator falls within our confidence interval. Just a gut check to see whether or not you're getting something interesting or not. But of course, more than that, now you're fully characterizing the heterogeneity. So this is the heterogeneity in people's responsiveness to interest rates. So it's like a price coefficient, if you will, right? Should be negative, and the confidence intervals give you an idea of what that average is, whether you look at their confidence intervals and ours.
That's only heterogeneity due to the axis, not due.
Yeah, it's cross-sectional data, remember. Right, so there is no panel, there's nothing else. It's just pure cross-section, but we can now characterize the heterogeneity across the cross-section using the observers. And that's what you're seeing over here. But there's also heterogeneity in all the advertising elements as well. Right? So just to give you an idea, this is a 13-dimensional treatment. So current kind of state-of-the-art causal approaches wouldn't give you a way of dealing with this easily anyway. Right? In this case, it doesn't really matter. And the data set is about 50,000 or so observations. It's not massive. And you get reasonable results which match up with what Sendel and Marianne already found. So this was more to kind of just gut check and say, do we get results that make sense from this framework? But we can go well beyond. So what was presented here are all the marginal effects. We just matched what. Now what I'm going to do is I'm going to say, okay, let's pretend like we want to do something of that typically a marketing or an IO person would do. Is like, I want to see if I can personalize interest rate offers. I've got this heterogeneity. What can I do with that? So I'm going to maximize a profit function. This is the loan amount. This is going to be the probability that you apply. Given an interest rate offer, that's the interest rate. This is the probability that you default. So, or your retention probability and prepayment probability. We do the math, you get kind of a first order condition. which then tells you what the optimal interest rate would be. And just like, in standard pricing problems, you get a fixed point problem because there's a logit involved. And so the optimal interest rate is defined by this fixed point. And again, we chose this to showcase the fact that even though the math is kind of tedious, it's a fixed point computation, we can just do implicit differentiation and get the influence function to just go through right away. So everything is automatic. You don't actually worry about anything at all. So here's kind of the idea of all those fixed points, and there's your confidence interval for the average interest rate. I can then take this interest rate, this personalized interest rates for every person, compute profits for that person, and give you what the expected profit increment would be, and give you confidence intervals for those. So just to give you, if you just think about what I've done, I've taken a standard problem, estimated heterogeneity, computed personalized interest rate offers, computed what the profits from each person would be, averaged those, and given you a confidence interval on that. Everything automatically. Any questions about this one? Okay. Yeah.
So is there any, usually when you use these machine learning, these causal inference kind of things, you'll use something like sample splitting or cross splitting or something like that?
We do that. Yes. So in the paper, I don't spell all of this out here, but in the paper, we recommend that you do sample splitting. It actually helps with stabilizing the results as well, because these machine learning things can be extremely noisy. So I can talk offline if you're interested in practically what you should be doing to implement these things. Like, you don't want to do something overly ambitious in terms of the deep nets, because theoretically you should have really large deep nets and then train this to infinity, right? But I'm assuming that most of you, at least graduate students, don't have till infinity to train these things. So you want to, do something reasonable. So smaller deep nets, which will characterize the same logic as having splines or polynomials or whatever else, right? You don't want something crazy because that'll be unstable. So you try and kind of reduce the complexity of your basis functions, if you will. Okay, so my second application in the next 10 minutes or so is one I'm excited about. It's partnered with the state of California's food stamp program. And in particular, let me just give you, so I'm assuming everybody here knows what SNAP is, but it's a program where people who qualify, so you have to be below a particular threshold in terms of poverty, you get a certain amount of money. It's about $176 per month per person, and it scales with how many people in your household. It's not easy to get qualified for SNAP. There's a bunch of hoops that you have to run into, and a bunch of people have kind of worked on this in terms of thinking about how to make this easier. I'm focused on a slightly different problem. After you've gone through the hoops and you've qualified for SNAP, 6 months later, you have to fill out this 2-page form. It's called a SAR-7. It's a semi-annual report. If you do not fill this form out, you will lose your benefits. Just to give you an idea, over 60% of qualified participants do not fill the form out, and they lose their benefits. And these are incredibly poor. Why? That's a whole other discussion, right? So Matt, one of my other colleagues, Matt Notovidigdo and Amy Finkelstein, had this paper where they talk about ideas like scarcity mindsets, where people are busy just surviving, and so it's really hard to think about filling out a form. Right? But I'm not going to go into that. My task is going to be, can we actually come up with interventions that get people to recertify at a higher rate? One of the things you can do, right, is send out a nudge. So this is the nudge that an organization called Code for America, that's contracted with the state of California, sends out just to remind people, hey, you're coming up on this due date, fill out this form, and you have to do it. And if you don't, you're going to lose your benefits. And what I'm going to ask is, how do we know that this particular language is right? What if I said this slightly differently? Would that be better? Okay. So the way you want to think about this is who picked this? Well, I tried to find out, and we don't know who picked that language, because somebody came up with it. But typically, when we want to come up with a nudge, somebody, some researcher or somebody, some analyst, just think about what's going to work and use the idea of what might work to pick a message from a feasible set of messages. That makes sense? So I could have said it a million ways. You have to pick one, and that's going to be this element here out of the gray area, which is all the possible messages that you could have said. Of course, the problem is that the nudge is going to a bunch of different people. So maybe you want to have multiple nudges, one for each person. Just like I just showed you with interest rates, why can't we do that with text messages or with email? The problem, of course, is I need to learn about people's preferences for language. But if I learned people's preferences for language, then I could just optimize language just like I optimize prices or anything else. That's easier said than done. So I'm just going to build a machine to do this. And the machine is going to have like 4 steps. You'll see how the framework I just developed is going to be useful here. First, I have to create a featureization engine. Then I'm going to stick it into my deep net, and then I'm going to do optimization just like we always do. So this is the nudge that was being said. The first thing I'm going to do is I'm going to steal an idea from Chomsky. It's called context-free grammars. It's actually used, I didn't know that Chomsky was influential in compiler design and in CS, but this is idea of how do you design a new language? So essentially, we can just create a new language because a language is just a set of rules. So my language is going to be constrained, and it's going to generate this 15,000 different things you can say, right? That's how, and how am I going to do that? This looks complicated. Think this way. Remember this thing where you mix up heads and torsos and legs and you get a different critter? Right? 3 binary features. If I say 101, you should see an English message. Right? 101 will correspond to John got on an airplane to Boston. 000 would be Mary got on an airplane to Chicago. It's bijective. So I can go from messages to data, from data to messages. And I couldn't do this with natural language processing and generation. It's not possible to do it, right? But this is stupid easy and it works. So I'm going to take this idea and I'm going to contextualize the snap message. So each component of the message, which was kind of done in partnership with the CalFresh team, gives you, so if you just go through the combinations, every combination will make sense. That's the rules of my grammar, that you have to go in order and pick one element from these things, and that'll give you about 14,000 or so different combinations. So that's my language.
So I'm thinking about the IRB process of this type of. So
it was an interesting problem where we had to have an argument because they wanted the treatment. And I was like, I can't give you the treatment because everyone is personalized. So each person could get a different message. It took a while, but yeah, so everything went through IRB. I pre-registered everything with the, whatever the AER registry is. So, but yeah.
I suppose you need to ensure that there is no combination that is going to get selected to be very effective, because there might be messages that are very effective. Snatch.
That is not a problem. So that is not a problem. Problem would be if there was some harm that could have.
Exactly.
But there was, so everything was detailed as to what we're going to do, and they were okay with it.
Okay.
Yeah, but it took months of argument. Okay, once I have the featureization, my model is going to be stupid simple, right? But you can see where the deep nets are going to show up. So each SNAP recipient has, I have a ton of data from the state of California about them because they have, these are all people who have opted in, they have shared their data, and they've actually said, like, if there's anything you can do to help me stay on SNAP, please do it. Right, so these are all people who have shared all of this data just for that purpose. So, but we don't have data, so we designed the experiment, and the design here has to be done carefully. You're not trying to do A/B testing. You're not trying to find the best message. You're trying to maximize information. So you use optimal design techniques from stats. There's a algorithm called the exchange algorithm, which basically finds points on the convex hull. You use those, you run your experiment, and you get a set of results. Here's the control. The first thing I want you to notice is that some randomly chosen messages are better and some are worse. Right? If you were doing A/B testing, you can see the problem. So this also kind of, I don't know if you're familiar with this paper that Stefano has on the ineffectiveness of like nudges that were done by governmental agencies. You can see why that might be, because if you're not doing this systematically, you can find these ones and you can get stuck there, right? And that's not going to be as effective as something that you optimized to find the best one. Using this data, we can estimate the model, just like I showed you before. With all the heterogeneity, these are the coefficients, or the expected coefficients. Here's the control message, which is nested in my framework as part of the language. And just to show you how this would work in 1 second, this is high as the baseline. The question is, should I choose hello on average? On average, you should, because the coefficient's positive. So if I keep doing that, I get the single optimal message, and it reads, hello, John, in order for you to keep your CalFresh benefits next month, you must fill out, it's cut off there, but your semi-annual report by October 11th, so on. So massive amounts of heterogeneity. Some people like hi and some people like hello. Again, I'm not a psychologist, so I cannot tell you why that happens. Some people like to be approached with a loss frame. Some people like to be approached with a gain frame. Again, I have no idea why, but it's all in there. Some people like a fixed date that they need to respond to. Some people respond to the fact that I need to do it as fast as possible. There's a question?
Yes, sorry, back to the previous slide. So basically you maximize the gradient before it's single input.
Yes. Yeah, so I see where your question is going. There could be complementarities between different elements. If you had the data and the bandwidth to pull it off, you can do it. It blows up, right? Combinatorial, this thing blows up very quickly. So my model is linear and simple. If you wanted to add quadratic terms, the number of parameters would just blow up, but you can do it. Remember, I'm constrained from a sample size point of view because I can't just get more people. It's only the people who show up, right? So I'm going to use October to estimate my model. That's what I get here. And then in November of 2020, we validate. Okay. So just to give you an idea, this is the predicted probability from 15,000 messages for one person. And that person has the best message. Different people have different messages. But I will always weekly do better than the control. Right? Because the control is nested in my language. So for some people, I'll do a little better. For some people, I'll do a lot better. This is in theory. In practice, who knows what happens? Okay, so in November, we implement the validation. Well, I call this doomsday validation, partly because of the fact that I had to, by law, send these messages out on the first Monday of the month, which was one day before election. Right? If you remember, there was this big election. What happened? Well, the model predictions were noisy, but we got about a 17.5% bump in recertification rates. That's not meaningful. So let me translate that data. In the data, so this is not a counterfactual projection. This is actually in the data. If you compute what the scaled outcome is in California, we're talking about $14 million more being disbursed because of this campaign. Of that, half comes from people who have zero income. So, and this is the increment over sending a nudge. So this is basically the deep net algorithm giving you the benefit, not the fact that you got a nudge. Right? Everybody would have gotten a nudge anyway. I presented this to the USDA. We wanted a scaled up number. So if you go across the US and did this one campaign in every state and scale that for the entire year, that would be about $12.5 billion more being disbursed to people who are poor. That's about 11% of actual disbursements. You can imagine the response to that. I don't think this is going to be implemented anytime soon. Some, like in California, they've put it into their apps. Other states are talking about it, but overall, not so clear that it'll actually get implemented. Okay, so I think I'm out of time, so I'm going to stop here.
Somebody can ask a question?
Yeah.
So, not in your snap experiment, which is cool, but, you know, if I went back to a standard model, I put in data X and I did your, then what would happen if I actually put in an unobservable in addition and then integrate it out with you?
You could do it. I have a.
The question is, does it change things?
Yes.
I mean, you get different numbers. So in a sense, it doesn't really, without that, I put it this way, it doesn't really encompass the models that are being used.
Yeah, so it depends on how you do it. I'll give you a great example. So there's a paper by Stefan Seiler and some co-authors that's coming out, which I'm writing a comment on in marketing science. What they did was they used machine learning techniques and they used Peter Rossi's like Bayes-M procedure to kind of do personalized pricing to see what profits would be. And they find that Bayes-M, the Bayesian kind of personalized pricing based on Bayes-M beats machine learning techniques. My point as a comment is that that's not theoretically possible, right? Because if you conditioned on all of the data and wrote down a non-parametric estimator, it should encompass the random coefficients model. So why did this work? I think it boils down to the featureization piece. So if you look at panel data, let's say, right, and you put random coefficients on, it's very, very clever and efficient in how it's using the full information across the observations. So a trick which they didn't do, which you can do, is if you have long enough panel like we do in marketing, if I take lots and lots of moments from your behavior in the past and then put those in, then I can eliminate the need for the random coefficients. I can show that. So it's a question of featureizing. If you don't do that, and you just want, you're going to have a parametric or a setup, and you're going to have random, then you can do random.
So I don't see how you do that if the X's are fixed and you don't put in an eta, a random variable.
Yeah.
A random variable, I can see how you fix it. But
Yeah, so the random variable you would put in, or that I put in, is your choices, in, like from a year ago, your average choices of each option of each brand.
Using it to back out an eta, unobservable.
Yeah, pretty much. If era I can be written as a function of past data, then you're putting in past data non-parametrically does the same job.
Yeah, but it doesn't do it for counterfactuals because now you've mixed up two things.
Agree. So I think I'm completely in agreement. So in that case, if you actually wanted to put in, you didn't want to do what I was saying, it's just not a data exercise, but you want to actually have a random coefficient in there, you can do that. So because adding random coefficients keeps everything smooth anyway, right? It's actually a smoothing device in some sense. So everything holds perfectly fine. So I'm way over time now, so I'm going to stop. The approach is simple, scalable, fully automatic, and like I said, it's doable with now standard software. So if you're interested, like hit me up, I can share code with you. You can tell me why it works or doesn't work.
Thank you.